So, what if I told you that one of the most powerful, most reliable tools in all of machine learning is basically built on the idea of, well, teamwork? Today, we're going to unpack random forests. And I know the name might sound a little intimidating, but the core idea behind it is something we all get. So let's just dive right in with the big question. Why on earth would you trust an entire forest over one single super smart expert tree? I mean, it seems a little counterintuitive, right? But the answer to this actually reveals a really deep truth about how to make smart decisions. All right, so to really get why the forest works, we first have to understand the single tree. And more importantly, we need to understand why having just one expert all by itself is often just not enough. I want you to think of a single decision tree as a brilliant expert. You know, it's great because it's so transparent. It can lay out its entire thought process step by step. But this expert, it has a huge hidden weakness, one that can make it totally unreliable when it really matters. And that weakness has a name. It's called overfitting. So imagine an expert who's just cramming for a huge exam. They've memorized every single question, every answer, from the study guide. They know it perfectly. But then they get out into the real world and face a problem they've never seen before. And they're completely lost. They memorize the facts, but they never really understood the concepts. That right there is overfitting. And this is really the heart of the problem. When a single tree looks at data it's already seen, its personal study guide, it looks like an absolute genius. Perfect scores all around. But in the real world, with brand new data it's never encountered, its performance can just totally fall off a cliff. It fails because it didn't learn, it just memorized. Okay, so if one expert is unreliable, what do? Well, you don't fire the expert, you build a team around them. And this is the huge idea behind what's called ensemble learning, or as we're calling it, the wisdom of the forest. And it all comes down to this really simple but incredibly powerful question. Instead of putting all our trust in one potentially flawed expert, what if we got a whole committee of them together and just listened to what they all had to say, collectively? And that is where we get the formal idea of a random forest. It's an algorithm that builds this huge forest of individual decision trees. You can really think of it as a committee of experts. And to make a final call, it doesn't listen to just one. Nope, it asks every single one of them to vote. So how does this committee actually decide? Well, it's actually super simple. If it's a classification problem, like is this email spam or not, the forest just takes a vote and the majority wins. And if it's a regression problem, like trying to predict the price of a house, it just takes the average of all the individual predictions. It's basically simple democracy, and it works incredibly well. But here's the thing, and this is really important. A committee where everyone is an identical clone, that's not very useful, is it? The real magic here comes from building a diverse team, where every member brings a slightly different point of view to the table. So how do we do that? Well, the secret sauce, it's right there in the name, randomness. The algorithm is designed to intentionally inject randomness into really clever ways to make sure that every tree in our forest is unique and not just a carbon copy of the others. Here's how it does it. First up, we've got data randomness. This is also called bootstrapping. So imagine giving each of our experts a slightly different stack of case files to look at. Some files might show up a few times, and some might get left out completely for that expert. Then you've got feature randomness. This means at every single point where a tree has to make a decision, we don't let it look at all the clues. We force it to only consider a random handful of them. And what you get from these two little tricks, well, it's actually kind of beautiful. You end up with a whole forest of decision trees that think differently from each other. They're less correlated. Each one has developed its own unique area of expertise, all because it learned from slightly different information and was forced to look at different clues. That's exactly what you want in a powerful committee. All right, so we've built our diverse team of experts. Now, let's get into exactly why this whole collaborative approach is so much better than that one lone genius we started with. The single most important reason is this idea of variance. So a single expert might have a really wild, unstable guess. But when you have 100 diverse experts, their individual mistakes, the ones who guess way too high and the ones who guess way too low, they all tend to cancel each other out. And this teamwork leads to a massive drop in variance, which gives you a final prediction that is way more stable and reliable. And this all comes down to what we call the bias-variance trade-off. A single tree has low bias, which is good, but it has that dangerously high variance.
A random forest makes this fantastic trade. It's okay with a tiny, tiny increase in bias in exchange for that huge, game-changing drop in variance. And that's what helps it perform so well on new data it's never seen before.
And get this, there's an awesome bonus power that comes with having this committee. We can basically turn to them and ask, hey team, out of all the different clues you looked at, which ones were actually the most helpful for making your decisions? This incredible insight is called feature importance.
So, for example, the forest could come back and tell us, hey, you know what? Customer age was consistently the most important factor in our decisions, while the number of website clicks, well, that was pretty much irrelevant. This gives us a real peek inside the data itself, which makes the random forest a lot more transparent than many other complex models.
Okay, so this all sounds amazing, right? But when should you actually use a random forest? I mean, like any tool, it's got its pros and cons, so let's get practical for a minute.
First off, the advantages. They're pretty hard to ignore. You get really high accuracy pretty much right out of the box. It's fantastic at handling messy, complex data. It's naturally resistant to that overfitting problem we talked about at the very beginning. And it's super versatile. It works for both classification and regression. But, of course, it's not all perfect. There are some trade-offs to think about. Building and talking to an entire forest of trees is naturally going to be slower than just dealing with one. It also takes up more memory. And while we can see which features are important, you can't really draw a picture of the entire model the way you can with a single simple tree.
And it's really because of this amazing balance of power and practicality that the random forest has become this go-to first choice for data scientists. When you've got a tricky problem and you just need a model that's robust, reliable, and performs well without a ton of tinkering, you call in the forest.
So look, if you remember just one thing from all of this, let it be this. A random forest harnesses the wisdom of the crowd. It brings together a whole bunch of simple decision trees and uses a democratic vote to come up with a final answer that's way more accurate and stable than any single tree could ever be on its own.
Which kind of leaves us with a final thought, doesn't it? This basic idea of combining lots of simple things to create something incredibly powerful, it's a cornerstone of modern AI. And it really makes you wonder, if a forest of decision trees can be this smart, what other kinds of crowds, what other forms of collective intelligence are just sitting there waiting to be found in the data all around us?